Okay, so complexity. Let's just go over our different types of complexity. So we have big O, we have little o, and we have, let's just check which ones we need to be aware of. Okay, so there's big O on here, there's omega, there is theta, and there's little o. Okay, so we've got all of these different measures asymptotically equal. I'm not sure that we need to. I mean, it's not like on the worksheet, and asymptotically equal. The only thing on the slides regarding that is that it's just strict to upper and lower bounds, but we've not been sort of told how to work that out. So we just need to be aware of big O and friends. Big O, little o, theta, and omega. So big O, G is an upper bound on how fast f grows as n increases. Little o is where we have a stricter upper bound than big O. That's where we have our limits. Theta is an upper and lower bound, which is given by the same function but with different constant factors. And omega is a lower bound on how fast f grows as n increases. Okay, so let's have a go at some questions, and then I think we can see where our weaknesses are from there. Okay, let's start with some big O ones. Let's have a go with this. Okay, so we want to show. I'll paste the full question actually. We want to show that f of n is an O of g of n. So how would we go about doing this? What would be our first step? So how I like to remember big O is, yeah, good. So how I like to remember big O is there exists some c and there exists some m, such that for all n greater than or equal to m, c times g of n, so c times n squared, is greater than or equal to our f of n, which is just 2n squared. So we need to find m and we need to find c, which satisfies this. Yeah, so yeah, I'd probably say n0 is better off here. Okay, but it shouldn't make a difference what you call your constants. It should be marked the same. So we want to find a constant, so some multiplier, and we want to find some crossover value. So this would be our n0, where our g function, so in this case n squared, is always going to be more than our. So imagine this is our f of n, this is our g of n. Our c would be the multiplier of this g of n function, and our n0 would be this crossover point, or anything above the crossover point. Okay, so how I like to find this is, this would actually be 2n squared plus 4. I like to just raise everything to that sort of, just make these all these coefficients of that, sorry. So 2n squared plus 4n squared is always going to be greater than or equal to 2n squared plus 4 for all values of n greater than or equal to 1. And so this gives us our n0, and this part gives us our c. If we group together these like terms, this just becomes 6n squared is greater than or equal to 2n squared plus 4, which looks eerily like this inequality. So our c is just 6, and our m, or our n0, is just going to be 1. And so we found two values for which this inequality here holds. Therefore, f of n is in O of g of n. Or we've proved f of 2n squared plus 4 is in, sorry, we've proved that 2n squared plus 4 is in O of n squared. Does that make sense in terms of big O? Let's have a go at one more question. So this one's involving a few logs and stuff. So again, there exists some m and there exists some n0, such that for all values of n greater than or equal to that n0, g of n, or c times g of n, c times n log base 2 of n, is greater than or equal to our f of n, which is this here. So 3n log base 2 of n plus 5n plus 8. Okay, so again, what I'd recommend is raising everything to this. So taking all of the coefficients of this and raising it to this. So if we have something like 3n log base 2 of n plus 5n log base 2 of n plus 8n log base 2 of n, this is going to be greater than or equal to 3n log base 2 of n plus 5n plus 8. But one thing to note is we can't just say for all n greater than or equal to 1 here, because log base 2 of 1 is 0. So that would make this 0. That would make all of this 0 and all of this positive, which means this inequality wouldn't hold. So we have to, in this case, consider what number it has to be at least for this to be greater than or equal to 1. So if we do log base 2 of 2, that is equal to 1. So this only holds for all values of n greater than or equal to 2. So that's what our n0 value would be in this case. So we found our, this should be c actually, yeah. So we found our c value. Our c value is just if we collect these coefficients, which is 8 plus 5 plus 3, which is just 16. And our n0 value would be 2 in this case. Why did you add log n to 5 and 8? The reason I added log n to these is just so that they're all the largest sort of polynomials, or that we just raise all of these, we take all of these coefficients and just multiply it by this polynomial term, the highest order polynomial term. And yeah, it's kind of trial and error. If you find a c and an n0, and then you find it doesn't work for this inequality, then try again. Try and find another c and n0 for which that inequality does hold. But ideally, if you use this sort of systematic method, and if you have a log or something, you'd use the base as the n, then you'd consider that. But yeah, we found a c and an n0, and so this confirms that this is in big O of n log squared, or log base 2 of n. Okay, so this is the mark scheme for the big O notation questions. So the idea is basically what we did. We found an n0 and we found a c. In this case, they found the same n0 and c as us. They found c equals 6 and n0 equals 1 by just adding up those coefficients, like this. And that's all we need to prove that it's in big O of n squared. We find that c and we find that n0. And then for question 3, we skipped question 3. For question 3, again, they found that n0 and that c equals 16. Note that this inequality does not hold for n equals 1, because log base 2 of 1 would be 0. So we have to take n as 2 in this case, because that's the case in which log base 2 of that n would be greater than or equal to 1. Yeah, because as soon as that's less than 0, it starts messing with those inequalities. Cool. Let's have a go at... Okay, let's have a go at this. So how could we go about proving that this function isn't in big O of n? So we want to show that there's no crossover point. So, okay, so we want to show that f of n is less than or equal to, or no, it would just be strictly less than, or no, even less than or equal to g of n for all values of n greater than or equal to m, or n0 for all values of c. Okay, so f of n not in O of g of n is a two-way implication that f of n is greater than c times g of n. And again, this is for some value of n greater than n0, because it might initially be less than it, but we want to show that there is some point after which it never crosses back. So if we have this function here, we want to show that after this point, this function is never going to overtake this one. It's always going to stay below this one, and this one's just going to be an upper bound. So how can we go about proving this? Okay, let's look at this. Right, so credit to Hux. For all values of n greater than or equal to n0, the differential of this g of n function, so this n, is greater than 0, because we know 1 is greater than 0. This differentiated is just 1. So that tells us that this is a strictly increasing function. And so this implies that our function f is in O of g, if and only if there exists a c and an n0 such that for all values of f, for all values f of n0, it's less than g of n0. Should this just be n? And this would be multiplied by c. But otherwise, yeah. So we want to show that this isn't true. So if this isn't true, yeah, so we don't actually need this can be n0, because we show that there is some point at which this is always going to be increasing. Yeah. So after n0, if it's always increasing, it's going to be true for all values of that after n0. Yeah, that makes sense. Okay, but yeah, how can we go about proving this doesn't exist, or there doesn't exist a c? I mean, we can tell that f of n, which is n squared, if we were trying to do n squared is more than or equal to n, if we were trying to do n squared is, or n is more than or equal to c of n is more than or equal to n squared for values of n greater than or equal to some n0, we know we wouldn't be able to do this. Imagine we divided both sides by n. We'd have something like c is greater than or equal to n for all n greater than or equal to n0. But we know that n can go up to infinity. So that means that c would also essentially go up to infinity. In terms of how it's been worded as a model solution, is that if we fix some arbitrary c greater than 0, and we compare f of n and c g of n, to find which values of n we have this inequality holding for. So say we have this, we just write out the function n squared is greater than cn, implies that n squared minus cn is greater than 0. So they've moved everything to one side and they've factorized n out. And that results in this. N times n minus c is greater than 0. Since n is greater than 0, the factor n minus c must be positive. So if this is greater than 0, then this must be, then n minus c must be equal to something positive. Because if this was anything negative, or this was 0, then this would be negative or 0. So this has to be positive. So n minus c is greater than 0. Moving the c to the other side of that inequality, we get n is greater than c. So n is greater than c, that's fine, because c is greater than 0. And so we can choose any n0, which is greater than c. So for all values of c, we found an n0 where this inequality holds, where this is not an upper bound for this. This is always going to be greater than this. So no matter what n0 we pick, for all values of c, for all possible constants greater than 0, we're always going to be able to find some n0 for which it isn't true, for which that inequality doesn't hold. And so we can say that f of n is not in O of g of n in that case. Right, let's have a go at this example here. So we want to prove that g of n is not in... That's a mistake. Okay, let's make that f of n. We want to prove that f of n is not in big O of g of n. So we want to prove that f of n is not in O of g of n. Okay, so it's kind of like a proof by contradiction. Assume there is some constant c such that there exists some n0 where for all n greater than or equal to n0, f of n is less than or equal to c times g of n. So we're assuming that there is some constant c. Then f of n would be in big O of g of n. Okay, we just have to show that this is impossible. We just have to show that there's no way this constant c exists. So f of n is less than or equal to c of g of n. So we're saying 5n cubed is less than or equal to c times n squared. This is our inequality. And we just want to rearrange this to show that C is dependent on this value of n. So similar to the other one, if we take away cn squared from both sides, we get this. We can factorize n squared out here, so n squared, and then we have 5n take away c is less than or equal to 0. We know n squared, any squared term is going to be greater than 0. So this is positive or equal to 0. And this has to then also be positive or equal to 0 for this inequality. Sorry, this has to be negative. So if this is positive and this whole thing is less than or equal to 0, this has to be 0 or it has to be negative. So 5n minus c is less than or equal to 0. And so this tells us that our c is greater than or equal to 5n. So if we choose some arbitrary constant c and then set our n0 to 5 times that constant, or anything greater than 5 times that constant, then that c is not going to hold. The c has to be greater than or equal to 5 times n0. And so we've shown that for all values of c, there does not exist an n0 such that for all values of n greater than or equal to n0, f of n is less than or equal to c of g of n. C times g of n, sorry. So the idea is we assume that there is a constant, work our way down until we get an inequality like this, saying c is actually going to have to be something dependent on n. And at this point we have our contradiction. And then we've proved that there doesn't exist any constant where there exists an n0 such that this inequality holds. Let's take a look at omega notation. So we have an upper and lower bound with omega notation. Omega is a lower bound, just a lower bound. So there exists a c such that for all n0 greater than 0, f of n is greater than or equal to c times g of n. So there's no n0 in this. We just assume that there does exist an n0 greater than 0, and we just have to show that for big enough values, g of n is a suitable lower bound for f of n. So let's take a look at this question here. We want to show that f of n is in, so show f of n is in omega of g of n. Okay, how would we go about doing this? Can anyone explain? Does anyone want to talk me through it? So if we think back to our definition, there exists a c, and there exists some n0 such that for all values of n greater than or equal to n0, f of n has to be greater than or equal to c times g of n. So all we've done is we've flipped this inequality, so it's omega. Instead of being less than or equal to, it's more than or equal to. So we just have to find these constants that satisfy this. 3n cubed plus 4n squared plus 5n plus 6 is always going to be greater than or equal to 3n cubed, for example. If we just take this term, without all of these extra added stuff, this is always going to be greater than or equal to this. Can we all see why that works? For all values of n greater than or equal to 1, this would hold. And so our c value would just be 3. C equals 3, and our n0 value can just be 1. So because we found these two values, very similar to big O, as soon as we found these two values, we've proved this whole statement here. There exists a c, there exists an n0, such that for all n greater than or equal to n0, f of n is greater than or equal to this lower bound, c times g of n. So that's how we'd prove that something's in omega of g of n. Oh, yeah, you're right. This should be n squared. So this would actually be something like this. And so you can change this to whatever number you'd like. I'd probably choose 4n squared in that case, just because if we imagine this term minus all of these terms, because we know all of the other terms other than this are positive. This is more than 0, this is more than or equal to 0. So this is essentially an obvious lower bound we can choose. In this case, our c value would be 4, and our n0 0 would work, yeah. But 0 might not work because it might not work with n equals 1. Actually, it would, yeah. So 0 would work in this case. Yeah, exactly. If we subtracted this from both sides, we'd just have these terms is greater than 0. And that's why this is a nice obvious choice. Good spot. So yeah, so it shows that f of n is not in omega of g of n. We can show that no matter how small we choose our constant c, c times g of n will always permanently overtake f of n from some point. So f of n is not in omega of g of n if and only if, for all values of c greater than 0 and there exists some n0 greater than 0, where for all values of n greater than n0, f of n is less than c of g of n. So, for example here, let's just have a go at this one. So we want to show that this isn't in omega of g of n. And so we can say, for all values of c, there exists an n0 such that for all values of n greater than or equal to n0, f of n is always going to be more than or equal to g of n. Well, actually, this would be a strictly more than, because it's the complement of omega, because it's the opposite of this. So we have to prove this. We have to show that for all values of c, there exists some n0 where this inequality holds. So n is greater than g of n squared. That doesn't... Wait. Okay, let me just double check that. Okay, so f of n is not in omega of g of n if for all c there exists an n such that for all n greater than or equal to n0, f of n is less than... Right, because this is a lower bound, so we want to prove that this isn't a lower bound, so it would actually be less than. Yeah, and I forgot the c there. So what this would actually be is... what this would actually be is f of n, which is n, is less than cn squared. And we just want to find that we can rearrange this to do something like 0 is less than cn squared minus n. If we factorize the n out, we can get n cn minus n, no, minus 1. This is more than 0. So if this is, we know n is positive, so this must also be positive. So cn minus 1 is greater than 0. So cn is greater than 1. Or c is greater than 1 over n. So we've shown that for all values of c, if we take 1 over n as our n0, I believe that's what we're showing here. Sorry, 1 over c. Okay, so n is greater than 1 over c. So if we take 1 over c as our n0, then this inequality holds. So we've shown that for all values of c, there exists some n0, 1 over c, such that for all values of n greater than or equal to 1 over c, f of n is always going to be less than cg of n. So this can't be an effective lower bound, because this is always going to be lower than this for some value. Okay, so for theta notation, we just have to prove that something's in theta. We don't have to really prove something's not in theta. So to prove something's in theta, let's take a look at this first question. Just to recap the definition, f of n is in theta of g of n if and only if there exists some c1 and some c2 and some n0, such that for all values of n greater than or equal to n0, c1 times the function is a lower bound for f of n, and c2 times the function is an upper bound of f of n. So let's have a go at this question. So we want to show that there exists a c1, there exists a c2, and there exists an n0, such that for all values of n greater than or equal to n0, c1 times g of n is less than or equal to f of n, which is also less than or equal to c2 times g of n. Okay, so let's see what we can do with this. We have this function here, our g of n is n squared. So something like 2n squared is always going to be less than or equal to 2n squared plus 4. Hopefully that's nice and obvious, because 4 is greater than or equal to 0. And to get an upper bound, we can use the same method we used with big O. So add the coefficients. Something like 6n squared is always going to be greater than this for all values of n greater than or equal to 1. Hopefully you can also see why that holds, because this would always be greater than or equal to this, because this is always less than or equal to 2n squared plus 4n squared for all values of n greater than or equal to 1. So we found a lower bound, we found an upper bound. Our C1 can just be 2, and our C2 can just be 6, and our N0 would just be 1. So because we found a suitable C1, C2, and N0, we've proved that f of n is in theta of g of n. We found a lower bound multiplier and an upper bound multiplier. So it's essentially it's just like we take this part from omega and we take this part from big O, and it just clumps it together. And the idea is it's the same function in the lower bound and the upper bound. We're just changing the multiplier of that function. Cool. Let's move on to the last type of notation we need to be aware of, little o notation. So the definition of little o is f of n is in little o of g of n, if and only if, as n tends to infinity, f of n over g of n exists and is equal to 0. Note that this definition does not require any choice of constants. It's literally just this formula, and we just have to work out whether it's equal to 0 or not. So let's try it. Let's try it with this top one. This is probably my favourite one. We want to show that f of n is in little o of g of n. So we want to show that 2n squared is in little o of n cubed, which means that as we lim n to infinity, f of n, so 2n squared over g of n, n cubed, is equal to 0, or exists and equals 0. Okay, how could we prove this? Oh, yeah, that 4 is also part of that f of n. Yeah. Okay, so one way we can prove this is we can split up all of these terms. So we can say this is the same as lim n to infinity 2n squared over n cubed plus 4 over n cubed. This is the same as factorizing this 2 out. N squared over n cubed becomes n, or 1 over n, plus 4 over n cubed, which is just 4 times 1 over n cubed. And then we can add a comment on the side saying as n tends to infinity, 1 over n tends to 0, and 1 over n cubed tends to 0. Therefore, this equals 2 times 0 plus 4 times 0, which is just 0. Therefore, f of n is in little o of g of n. Let's have a go at this. We want to show that f of n is in little o of g of n. Okay, so as lim n tends to infinity, and then we're going to have this, so f of n plus 8n squared plus 7n plus 6 over g of n, n to the 4. We want to show that this is equal to 0. So it equals lim n to infinity. So let's split up the terms again. 9n cubed over n to the 4 plus 8n squared over n to the 4 plus 7n over n to the 4 plus 6 over n to the 4. Again, just to make it explicitly clear what's becoming 0, we can factorize the terms out. So this would be 9n cubed over n4, or this is the same as 1 over n, plus 8, 1 over n squared, plus 7, 1 over n cubed, plus 6, 1 over n to the 4. And then you can just add another comment. As n tends to infinity, 1 over n tends to 0, 1 over n squared tends to 0, 1 over n cubed tends to 0, and 1 over n to the 4 tends to 0. Therefore, this is just equal to 9 times 0 plus 8 times 0 plus 7 times 0 plus 6 times 0, which is just 0. Therefore, f of n is in little o of g of n. Hopefully that's clear. Okay, so I see someone asking, what if it isn't in little o? So to prove that something's not in little o, all it means is as we take that limit, it's not equal to 0. So let's say we had something like this, and we want to show that this isn't in little o of g of n. So again, lim n to infinity, f of n, so 2n squared plus 4 over g of n, which is just n squared, equals lim n to infinity, and this can become 2, this will become 2n squared over n squared plus 4 over n squared. Hopefully we can all see this 2n squared over n squared just becomes 2. As n tends to infinity, 4 over n squared tends to 0, or we can even just say 4 times 1 over n squared tends to 4 times 0, which is just 0. So this would become 0, and so we'd be left with just 2. We wouldn't have 0 here. And so because this is not equal to 0, then that's sufficient proof to say f of n is not in little o of g of n. Our other case is if we had something like f of n, I'll do it in a different colour. Other case is if we had something like f of n equals 2n squared plus 4, and g of n is equal to n. So if we did something like this, so it could also be infinity. If we did lim n to infinity 2n squared plus 4 over n, this would be equal to lim n to infinity 2 over n, no, not 2 over n, 2n over 1 plus 4, which is just 4 over n, which is just lim n to infinity 2n plus 4 times 1 over n, and then we can say as n tends to infinity, 1 over n tends to 0, n tends to infinity, so this would become 2 times infinity plus 4 times 0, which is just infinity, which is not equal to 0, therefore also in this case f of n is not in little o of g of n. Cool. Oh, yeah, my bad. There we go.